Welcome to Lesson 4. We'll be dividing powers of 10. We'll specifically be exploring patterns with exponents when we divide powers of 10. And to be successful in this lesson, you'll be able to explain and use a rule for dividing powers of 10. You'll also be able to evaluate 10 to the power of 0 and explain why it makes sense. The first activity, a surprising one, gives you an expression. Take a moment, pause your screen, and think about what is the value of that expression. Now that you had some time to think, let's talk about some strategies. It's possible that some of you maybe evaluated the entire numerator and denominator, and if you did that, you would have seen something like this. It's also possible that some of you maybe listed out all of the factors for the numerator and denominator, and if you did that, it looked something like this. Now, they're color coordinated to show you how many factors of 3 are in the numerator and denominator and how many factors of 2 are in the numerator and denominator, which happen to be the same. And very similar to the first strategy, both of these are equal to 1. Keep this in mind because this is going to be a reoccurring theme as we continue through the lesson. So let's just talk about making use of structure before we move on. By matching factors from the numerator and denominator, that helps you show the multiplication by 1. So here's just another example. So if we rearrange the numerator and denominator to kind of show those matching pairs, you see that 3 times 7 times 11 is seen in the numerator and denominator. And we know that dividing something by itself gives you 1, which leaves you with 2/5. So again, keep that in mind because we will be looking at the structure of these expressions throughout this lesson. So going into the next activity, we're going to look at dividing powers of 10. And we start with a very familiar table. You've seen these in the last several lessons with the expression column, the expanded column, and then that single power. Before you pause and work, let's just notice some things in the expanded column. The expanded column shows each power of 10 expanded into factors. So the division is written as a fraction, and a certain number of factors in the numerator and denominator being grouped because their quotient is 1. So what do we mean by that? Well, if you look at that numerator and see those two factors of 10, pair up with those two factors of 10, which is written in this next piece of the expanded form. But you're also left with the other two factors of 10 that still get multiplied, which you see there. Just like we did in the warm-up, we know that 10 times 10 divided by 10 times 10 gives you 1, which is what you see in that very, very last piece of the expanded form, hence why it's 10 squared. Take the time to go through the rest of the components. You do get the option to skip a single box, just like the last couple that you did. So if you choose to do that, just make sure you can back up your reasoning as to why you did that. So go ahead and pause and continue working on the box as well as questions 2 and 3. Okay, now that you've finished working on your table, let's go through what each of these components should look like. So the next row that we have would be written as 10 to the 5th divided by 10 squared. You see those 5 factors of 10 in the numerator and the 2 factors of 10 in the denominator. And based on the expanded form, we would say that the single power is 10 to the 3rd power. And the next one, we have to write out that expanded form. So we start with 6 factors of 10 in the numerator and 3 factors of 10 in the denominator. And if we think about pairing up those factors of 10 in both numerator and denominator, there's 3 of them that we can group together. And then we're also left with 3 more factors of 10. We would write that as 10 times 10 times 10. I'm actually missing the 1 there, but there would be a 1 in front of that to just have consistency with the rest of the table. But this also would be 10 to the 3rd. Now you might have started to notice patterns already, and when you got to this last one, you might have said you're skipping this one for some very obvious reasons. If you chose to skip that, great. If you felt like you had to write it all the way out, let's hopefully create that rule so that way we're not having to expand so many factors. So as you start to look at the patterns from row to row, you if you look at that expression and then look at the single power, the pattern we start to see is that we're actually subtracting those exponents. So in this last one, we would say that it would be equal to 10 to the 26th power. So let's just put this rule into perspective with question 2. So using the patterns we found, let's rewrite 10 to the power of n over 10 to the power of m. And we would now say that it's 10 to the n minus m for any exponent that we would have in place of those variables. The last question relates this to a real world situation. It says it's predicted that by 2050, there will be 10 to the 10th people living on Earth. At that time, it's predicted that there will be approximately 10 to the 12th trees. How many trees will there be for each person? So again, just conceptually thinking about what operation am I using here to evaluate this? And we are using division. So the number of trees divided by the number of people is going to tell us how many trees per person. So 10 to the 12th divided by 10 to the 10th, if we apply what we just talked about, we would get 10 to the power of 2, or 10 squared. So let's just discuss some things here. Let's say we want to write 10 to the 6th divided by 10 to the 3rd with a single power of 10. What happens to the 3 factors that are 10 in the denominator? Well, those 3 factors that are 10 in the denominator are matched with the 3 of the factors that are 10 in the numerator. Then you would divide to make 1. And how many factors that are 10 are left in the numerator? And that would be 3 factors. So let's just have a visual of what that means. So here's the 10 to the 6th divided by 10 to the 3rd. If you list out those factors, you see that there's 3 factors of 10 in the numerator, 3 factors of 10 in the denominator that would divide to equal 1, which leaves you with 10 to the 3rd. So just revisiting the criteria, we want to be able to explain and use a rule for dividing powers of 10, which we already just discussed in this activity. And now we'll be evaluating 10 to the power of 0 and explaining why it makes sense for what we're about to see. So as we move into the 0 exponent, we've so far looked at powers of 10 with exponents greater than 0, but we want to see what would happen to our patterns if we included 0 as a possible exponent. So keep in mind all the rules that we have already discussed. You're going to work on questions 1 to 4 first. Go ahead and pause the video and do that now, and then when we come back, we'll discuss each of those components. Question 1 starts with 10 to the 12th times 10 to the 0 and you're trying to essentially find a power of 10 with a single exponent using the appropriate exponent rule. So this takes us back a few lessons ago where we talked about adding exponents in a situation like this. So we would think about this as 10 to the 12th plus 0. Didn't want all of that to show yet, which is equal to 10 to the 12th. But then it asks, what number could you multiply 10 to the 12th by to get the same answer? And anything times 1 gives you itself. So we could say that 10 to the 12th times 1 is equal to 10 to the 12th. So just start to notice some relationships here from that first line to the last line. Let's move on to the next one. Write 10 to the 8th over 10 to the power of 0, or divided by 10 to the power of 0 with a single power of 10 using the appropriate exponent rule, which would now be to subtract the exponents. So 10 to the 8th over 10 to the 0 would be equivalent to saying 10 to the 8 minus 0, which would just be 10 to the 8th. But then it asks you, what number could you divide this by to get that same answer? And that also would be to divide by 1. That's going to also give you 10 to the 8th. So again, notice the relationship between the first expression all the way down to this last one with the red, and start to notice what 10 to the power of 0 might be equal to. So if we want the exponent rules we found to work even when the exponent is 0, then what does the value of 10 to the 0 have to be? The value of 10 to the power of 0 has to be 1 in order for the exponent rules to work when the exponent is 0. So we'll, from now on out, say that 10 to the power of 0 is equal to 1. Noah says if I try to write 10 to the power of 0 expanded, it should have 0 factors that are 10, so it must be equal to 0. Do you agree? Noah's answer appears to make sense with how we first defined exponents, but if we want to be able to use the exponent rules when the exponents are not positive, we have to define it differently. So how can we write something like this? 10 to the 36th power over 10 to the 12th using a single exponent. So we have a rule now that we will subtract those exponents, and that would give us 10 to the 24th power. It's a common mistake for students to try to divide the exponents. Why do we subtract the exponents instead of dividing them? The exponents are subtracted because we are counting the number of factors that are 10 that survived the division. And when we mean survived the division, think about the factors of 10 that paired up from numerator to denominator. When you divided those, they were equal to 1. The remaining factors is where we were coming up with that single exponent, how many were left. Why did we define 10 to the 0 to be equal to 1? So that it fits with the exponent rules we have discovered for positive exponents. That's why we defined it today. Your lesson summary is there for you to breeze through if you would like to. Otherwise, you are successful after this video if you can explain and use a rule for dividing powers of 10, and if you can evaluate 10 to the power of 0 and explain why it makes sense.